This week, we're going to continue with sequences, but look at a type of sequences called geometric sequences. The kind that we worked with last week were arithmetic sequences. Here's the situation. You drop a ball from the bleachers that are 16 feet high. Each time the ball bounces, the height decreases by half of the previous height. After one bounce, the height of the ball is 8 feet. I'm going to make a table showing the height of the ball after each bounce. It starts at 16 feet, so after 0 bounces, it's at 16 feet. After one bounce, it goes up to 8 feet. Then it goes half, 4 feet. Half of 4, 2 feet. Half of 2, 1 foot. Half of 1, 1/2 foot. Each number is half of the number before them. This is not an arithmetic sequence. In an arithmetic sequence, each number has to have the same thing added or subtracted to it to get the next value. We can write a recursive rule for this, and we kind of said it in the problem. And we said that each time it goes half as high. So what are we going to do? There's 2 ways we can write this. We can say that you multiply the previous value by 1/2. Which is the way that when we get to our formulas, we're going to want to think about this. But we could also look at these numbers, 16, 8, 4, and 2, and think that you were dividing. Another correct recursive rule would be divide the previous value by 2. Now, these two things mean the same thing because remember, division is the same as multiplication by the reciprocal. Dividing by 2 is the same as multiplying by 1/2. The next thing we're going to do is make a graph of this relationship. So we're going to graph the relationship between the height and the number of bounces. I already have the axes labeled. On the x-axis, we're going to put the number of the bounce, and on the y-axis, we're going to put the height of the ball in feet. So after 0 bounces, it's at 16 feet. After 1 bounce, it's at 8. 2 bounces, it's at 4. 2 bounces is over here. 2 bounces is at 4. 3 is at 2 feet. 4 is at 1 foot. And 5 is at 1/2 foot. And what we see is we get this curved shape to these points. This is something that you see with geometric sequences. One way we could describe this is to say that it looks like a quarter pipe, quarter of a circle. If you graph arithmetic sequences, they are linear, which we didn't look at very much, but you would get a different shape than the geometric. Here's our definition of a geometric sequence. A geometric sequence is a sequence of numbers where each value is found by multiplying the previous one by a common ratio. How do we check if the sequence is geometric? We divide each value by the previous one. In this example, 6, 18, 54, 162, 486, if it was arithmetic, it would go up by the same number each time. 6 to 18 goes up 12. This obviously does not go up 12. To check if it's geometric, we take the 18 and divide it by the number before it. Divide it by 6, and you get 3. Take 54 and divide it by the value before it. You get 3 again. And we could continue. 162 divided by 54 is 3. This is a geometric sequence because there is a common ratio of 3. Over here, 20, 10, 5, 2.5, 1.25, again, we're not adding the same number, but if we divide 10 divided by 20, I get 1/2. 5 divided by 10, I get 1/2. 2.5 divided by 5, I get 1/2. You could say that the common ratio is 1/2 or the common ratio is 0.5. We are going to write explicit formulas for geometric sequences, just like we did for arithmetic sequences. The steps are find the constant ratio, divide one value by the one before it. we're going to raise the constant ratio to the n power. There's going to be an exponent in these equations. We're going to find the value of the zero term and then multiply the constant ratio by the zero term. For example, 8, 16, 32, 64, 128. If we divide a value by the one before it, we try this a couple times, we see that it is consistent. So this is a geometric sequence with a constant ratio of 2. So going forward, you multiply by 2 to get the next value. If we multiply by 2 going forward, then to go back to the zero term, we have to take the 8 and divide it by 2 to get the zero term of 4. The explicit formula, you take the constant ratio and raise it to the nth power, and then you put the zero term and multiply that by it. We're not going to plug in any numbers for n today. When we have to do that tomorrow, I'll talk about calculators. Here's another example. I have 9 divided by 1 is 9. 81 divided by 9 is 9. And if I kept going, that ratio would be constant. It's a constant ratio of 9. I am always going to put the constant ratio in parentheses. That is very important if I'm plugging in a negative number, but we're going to do it for all the numbers to be consistent. So I go times 9 as I get bigger. Going backwards, I divide by 9, so my zero term is 1 divided by 9. And you can leave it as that fraction 1/9. If you put that in your calculator, you're going to get 0.111111. We'd rather leave it as exact as 1/9. Here's another one. This one's going down, 100, 50, 25. I want the constant ratio. I want to know if I take one value and divide it by the one before it, what do I get each time? The constant ratio is 1/2. We need to write this, think of this as multiplying by 1/2 in order to write the formula. We cannot think of it as dividing by 2. So if I multiply by 1/2 going this way, going backwards, I would divide by 1/2. So now I need to flip it. Dividing by 1/2 is the same as multiplying by 2. The number before 100 should be 200. Zero term goes first, the ratio goes inside the parentheses, and the n is the exponent. Just so you know what you're doing at the very first part of the homework today, in this case, you're asked to circle whether the sequence is arithmetic, which means it has a constant difference. You add or subtract the same number each time. Or if it is geometric, where you're multiplying by the same number each time for a constant ratio, or neither. If it is arithmetic or geometric, then you write the recursive rule. If it's neither, you can just move on. So when you look at these, some of them, I should check. Am I going up by the same number each time? No, this goes up 3, then up 6. Am I multiplying by the same number each time? If you're multiplying by the same number each time, it's geometric, and your recursive rule is to say, multiply the previous value by 2. And some of them, we're going back to what we did before last week. 10, 20, 30, 40. This one goes up by the same amount each time. This is our constant difference. This is arithmetic, and the recursive rule is add 10 to the previous term. To give you an example of neither, if we look down here, I check and see if it goes up by the same amount. This goes up 3, up 5, up 7. It's not arithmetic. I divide and I say, okay, is 4 divided by 1 the same as 9 divided by 4? No, this is a neither. There's a different pattern for this. And if it's a neither, you do not need to write a recursive rule.